Hi everyone, welcome to another video for research design and analysis. In today's video, we're going to be talking about t-scores and the t-distribution and how we can use the t-distribution to calculate the probability of observing certain t-statistics in our sample. So this builds off of the previous videos where we were talking about the normal curve and using z-scores to perform a similar function, but now we're going to be talking about t-scores because, as we talked about previously, one of the issues that we face when dealing with sample means is that the distribution of sample means will often only be approximately normal. It won't actually be truly normal, making any calculations we do using the normal distribution slightly to very inaccurate. So we need to be able to understand the t-distribution and use it accordingly. But first, let's just think about finding the probability of an event in a normal distribution. So not necessarily a sample mean, but let's just say the probability of getting like a certain score. Right? So if we're thinking about intelligence tests, right, again, they're kind of a nice example because by design they have a population mean of 100 and a population standard deviation of 15. We could ask, what is the probability of having an intelligence quotient greater than or equal to 130 on this specific test? Well, there are a couple different ways we could do this, right? The first is, if we had all of the data, we could solve this in an empirical way. So if I had access to the whole population of people with intelligence test values, right, I could just count the number of observations that are greater than 130, and I could divide by the total number. The kind of alternative calculation here would be theoretical. So we don't necessarily need access to all the scores, but we have to understand the shape of the distribution. And if I know the shape of the distribution, then I would just need to take the integral of it to find the area under the curve less than 130, and I could divide that by the total area to get, the proportion under the curve to the left of this cutoff and the proportion under the curve to the right of this cutoff. Or by the same token, right, if I actually know the distribution, then I probably know something about the cumulative density function of that distribution, and I can find, the number of scores greater than 130 that way. But in essence, right, the empirical approach requires us adding up all the data and, manually counting in some way. The theoretical approach allows us to derive these probabilities based on our knowledge of the distribution. So if we do have a standard normal distribution, right, that's something that we're relatively prepared to work with given what we talked about in the previous videos. We can take any observed score, use the z-transform to turn it into a z-score, and then we can solve for the probability assuming a normal distribution for z. Now in this case, right, we have 130 minus 100. That's the difference between our score and the observed mean. Our standard deviation is 15. So that translates into a z-score of 2. And then we would have kind of two different probabilities we could calculate here. We know that the total area under the curve is 1 because that's the probability of all possible scores, right? But we could get the left-hand tail, right, which is to the left of our cutoff, or we could get the right tail, which is to the right of our cutoff. And in this case, because we're saying greater than or equal to 130, we want to know what's in the right-hand tail. And it turns out that if you solve for this, that is 2% of the data will be greater than or equal to a z-score of 0.2. Now, recall from our previous video lectures that the distribution of sample means is only approximately normal. But the nice thing is that this is true even if the parent distribution is not normally distributed. So by the central limit theorem, we know that regardless of what the parent distribution looks like, as long as we're talking about sample means, the distribution of those sample means is going to become more and more normal the larger our sample size gets. And this is awesome because it allows us to calculate the probability of observing a sample mean even if we don't know anything about the population. And that's really key because oftentimes we have pretty limited information about the population. So this becomes very, very useful. Now, the trick in this, right, is what we mean by approximately normal. Okay, so again, if we're taking a sample means here, like here's our population. So let's say that a hypothetical intelligence test had a uniform distribution of scores between 0 and 200. Now, if I'm taking samples of size 10, the mean of sample means is going to be a good approximation, or it's always going to be an unbiased estimate of the true population mean. So this is centered on 100. When I'm taking samples of size 50, that's also centered on 100. So you can see that both of these distributions of sample means are centered on 100 and they are symmetrical. The problem, though, is that when we're making this calculation for sample means, it's only approximately normal when n is relatively small, and it's going to approach normality when n gets bigger and bigger. So one of the things we have to contend with is that the standard error for this distribution is changing as a function of the sample size. right? And you can remember that the standard error is really just a special case of the standard deviation. Specifically, it is the standard deviation of the sample means. So I can get that the standard deviation of each of these distributions obeys whatever the population standard deviation is divided by the square root of n. Now, the issue though, right, again, is that although we can get that standard error and we know that this is going to be approximately normal, how normal is it? So we can actually show this, rather than mathematically, we're just going to kind of show this visually. So we're going to look at the density of obtaining a particular t-value on the y-axis as a function of what that t-value is on the x-axis, and then we're going to change the sample size. So as a starting point, let's think about when n equals 3. Now this certainly looks like a bell curve, but it's not actually a perfectly normal bell curve with respect to the statistical definition of what a normal curve is. And we can see this changing if we change the sample size. So now let's say we're taking a sample of size n equals 10. You can see that the tails are getting a little bit narrower, and there's a little more mass in the center of this distribution. As we go to size 50, again, you can see the tails get a little bit narrower and a little more mass is added to the center of this distribution. And now if we theoretically took an infinite sample, it's going to approach normality. So this gray line here is actually a perfectly normal curve, which this distribution is going to approach as we increase the sample size. So this distribution that changes as a function of the sample size is the t-distribution. And you can see that it looks a lot like the normal distribution as we walk from the black curve to the red curve to the blue curve to the gray curve. The difference is the t-distribution has thicker tails and has less mass in the center of the distribution than the normal curve, which means our calculation of the probability of certain events is going to change. Because again, the amount of data in those tails, right, changes the probability of obtaining a score beyond a value of 2. So you can see, beyond any number, but let's look at 2 as an example, right? So draw a line up from 2. Think about the area under the curve for the gray distribution versus the black distribution. Having that fatter tail means there's a lot more area under the curve in those more extreme t-values when n is 3 compared to under the normal distribution. So if we were using the wrong distribution to make these calculations, we're potentially going to be pretty inaccurate in the p-values that we calculate. That is, unless the n starts to get pretty big. So, for that blue curve, when n equals 50, you can see that it actually starts to be a pretty good approximation of the normal distribution. So as your sample sizes get larger, we have to worry less about this. But in general, we're going to use the t-distribution because it's going to change its shape based on the amount of data that we're taking. And again, its shape is similar to the normal distribution, but it varies based on the number of observations. Now, we can use this distribution in exactly the same way, right? Similar to how we calculated z-values, we can now calculate t-values, and they're going to tell us how far away the sample mean is from a hypothetical true mean in units of standard error. So if sigma were known, right, we could calculate a t-value in a really similar way to calculating a z-value, where we're looking at the distance between a sample mean, x, and a hypothetical true mean, mu, and we divide by sigma over the square root of n to get the true standard error if sigma were known. In practice, however, sigma is usually not known. So what we're going to have to deal with is estimating sigma using the sampled standard deviation s. In previous videos, we've talked about how to calculate s with the appropriate degrees of freedom so that it becomes an unbiased estimate of the population standard deviation. So this is a kosher move, right? And if you don't remember how we did that, you can refer back to some of our previous videos. But in essence, we're going to know what the mean of our sample is, and we're going to know what the mean of our standard deviation is, but we won't necessarily know what the mean of the what the standard deviation of the population was. So we have to estimate it using S. And this is the formula that we will use moving forward to calculate t-scores within a sample. So now, armed with that knowledge, we could say, what is the probability of observing a sample mean in a t-distribution when n equals 10? So again, let's assume we're talking about these intelligence tests where there was a mu of 100. We don't know what the standard deviation is in the population. So we're going to get an x bar of 115, and in our sample we observed a standard deviation of 30. And again, this is a sample of size 10, so we can use that to calculate a standard error where we take s divided by the square root of n. That works out to be about 9.5, right? And then we can take the difference between the mean in our sample, the mean in our population, and we can calculate a t observed. So the t observed for 9 degrees of freedom here is 1.581. Now, we can think about this drawn on the appropriate t distribution. So this is the t distribution when there are 9 degrees of freedom. And again, this is going to have thicker tails and a shorter center than the normal distribution. But if we want to know what is the probability of getting a sample mean of 115 or greater, we could place our t observed value on this curve and then look at the area under the curve for that t observed value. And in this case, if we solve for the probability of getting a t of 1.581 or greater when you have 9 degrees of freedom, that's a p of 0.74. So we would expect a t observed value of this size or greater about 74% of the time due to sampling variability alone under the null hypothesis, right? So assuming that the true distribution is centered on 0, that we would expect to get means of that size or greater about 7.4% of the time when the sample size is 10. Now, what if we change one aspect of this and we make the sample size 50? Well, the mean we observed in our sample stays the same. The standard deviation we observed in our sample stays the same. But now the standard error is going to get smaller, right? Because we're taking the same standard deviation and dividing it by a much bigger number. That leaves us with a standard error of 4.243. And that in turn is going to give us a much bigger t value, right? So this is a t with 49 degrees of freedom, and the t observed now is 3.536. So the same difference between means looks a lot bigger now because the standard deviation is smaller given the larger sample size. And again, if we were now to draw a t distribution based on 49 degrees of freedom, what we're going to find is, we can place our t critical value, which was again 3.536 over here, and you can see a lot less of the curve is to the right of that critical value. So the probability of getting a t of 3.536 or greater looks like it should be pretty small in this situation compared to when n was just 10. And indeed it is, because if we solve for the probability of getting a t value of this size, right, the area under the curve to the right-hand side of that is only 0.0045. So we'd expect to observe a t value of this size or greater, less than 1% of the time now, due to sampling variability alone when the sample size is 50. So the same difference in terms of the difference between the sample mean and the population mean can take a different p-value, right? Because again, the t-value doesn't tell us about the absolute difference between the sample mean and the population mean. It tells us about the difference between these two things with respect to the standard error. So when the standard error gets smaller, this mean now looks a lot more extreme, and indeed we're a lot less likely to observe a mean of that size under the null hypothesis. So as a generalized form of the t-statistic, we can think about this as this t observed as a function of a particular value we will obtain in the sample. So I'm writing this as a b with a little hat to indicate that this b is being used to estimate some parameter in the population. And we're going to be comparing it to some hypothetical true value of the parameter. So, right, b is our statistic, beta is our parameter that we're trying to estimate, and in this case I'm putting a subscript h on that beta to indicate that this is a hypothesized value of beta. So sometimes these might be sample means, other times these might be slopes, right? There are a lot of things that these could potentially be, but we're always going to be looking at the difference between these two values with respect to their standard error. So, for instance, we could think about this as if we assume that the mean resting heart rate is 68 beats per minute for healthy young adults, and then we observe a mean heart rate of only 60 beats per minute in a random sample of young adults. How likely is it that this result occurred due to sampling variability alone? Well, the answer is going to be that it depends, right? We don't actually have enough information to completely solve this problem. So we know that we observed a mean beats per minute of 60, and we have a hypothetical mean beats per minute of 68. So we know that this is below the hypothesized value. But how far below is it? Well, we need to know the standard deviation and we need to know the sample size in order to calculate the standard error. Because if this standard error is large, this 8-point difference might not be very meaningful. But if this standard error is small, then an 8-point difference might actually be very unlikely. So the same difference could lead us to potentially different conclusions. For instance, if the standard deviation was 12 and n were only 5, then we could solve for the standard error and ultimately solve for a t observed, which works out to be negative 1.49. In contrast, if the standard deviation was 12 and n is 20, then the t observed for this difference is negative 2.98. So by adding more observations and shrinking the standard error, I make the same mean difference look a lot more unlikely in 20 subjects than when I observed that mean difference in only 5 subjects. Therefore, the surprisingness, right, of this effect depends on the size of the effect, right, the magnitude of the effect up here in the numerator, the variability of the data captured by the standard deviation, and the size of our sample captured by the square root of n. And the larger these t-values are in either the negative direction or the positive direction, the less likely we think these events are to have occurred due to sampling variability alone. Okay, so I know that's a lot to kind of throw at you, but again, this is our introduction to calculating the t-statistic in our sample, and we're going to get into more detail in the subsequent lectures about how we can use that t-statistic to then make inferences about parameters in the population. Again, though, the same logic that we've always focused on applies in that we're going to have a lot of factors at work to shape our conclusions. And the effect size, right, is one of those things that help us think that, okay, perhaps there is actually something systematic going on in our data. If we increase the sample size, again, that's going to help us make us more sure. If we increase the variance, that's going to make us less sure. And then how sure do we need to be, right, is what we're going to actually talk about in the next couple lectures. And we'll talk about where do we set kind of the threshold for evidence in a decision-making process where we say, hey, this statistic is too large. We don't think it occurred due to sampling variability alone. Or we say, hey, this statistic is pretty small. It could very well have emerged due to sampling variability, and therefore we might be less sure of what to make of it. And we have a more equivocal result if that's what we see in our data.